because this is going to be one of the outcomes of a European project which is called FitHydro. It's about fish-friendly innovative technologies for hydropower. So how can we improve a lot of the existing hydropower in Europe to the benefit of fishes without compromising the production of hydropower? Quite complicated task. It's a lot of partners in Europe. This project is led by Technical University of Munich. And you can see there's a lot of partners, both from research and universities, from hydropower companies, and from consultancies. So we're trying to work together on this. And this is the background for what I'm going to present to you now. The whole idea is built up that we need to have some tools, some methods, some devices to help us and to find the solutions. Things like, of course, these are things we are working on, all of us, I guess, within Ecohydraulics, like laboratories, numerical modeling, and also testing it in the field, all these methods and tools and so on. And of course, an important part is that we have to try to bring some new knowledge and ideas into it. Maybe they're not new, but maybe we can take them from other disciplines and other sciences. So this is how we are working. A major part of the work is actually going on in what we call test cases. I'm not sure if you can see all the small yellow dots on this screen, but that's supposed to be the test cases. They are either in the Iberian region, Spain, Portugal, France, Belgium, the Alpine region, and in Scandinavia. And most of the test cases are like most of hydropower plants in Europe and most of hydropower plants worldwide. If you count the numbers of hydropower plants and rivers, it's not the big ones, it's the small ones. That's the number. Of course, the large hydropower plants, those produce most energy. But if you look at how many rivers are impacted by hydropower, you will find that most of them are impacted by small hydropower schemes, like some of these on the picture. Not all of them are very small, but we're not talking about those mega projects that you might find around the world. In this, and that's maybe where we also have to put our efforts. These are the places we need to improve conditions. So what can we do if we have a hydropower plant or a hydropower impacted river to mitigate? Of course, we can use water in another way. When we have a reservoir, we can regulate the water. We can use it in another way. And we can, of course, also do physical measures, meaning going out with an excavator and building things in an already impacted river, building a fishway, or trying to enhance habitat and substrate conditions for fish, and so on. When we are doing that, we have to keep in mind, if we're doing this for fish, that's the main focus of our work now. We want to enhance or make sure that we have a sustainable fish population. And we have to know that growth and survival of fish, of course, depends on the number of fish in an area and also the available habitat. What I'm trying to say that if you kill one of these fishes, it's not for sure it has a population effect. And on the other hand, if you kill just one of them, it might have a huge effect on the population as well. The thinking here is that we have to look for some kind of a bottleneck. If you look at a typical, I guess this graph is from salmonids that also migrate to the ocean. If you look at the life strategy of, for instance, this kind of fish, is that you have many offsprings, and maybe out of 1,000 eggs, in the end there will only be one salmon coming back to the river as a big adult, right? And it goes through several different phases, several different life stages, several different times of the year, with specific requirements of its habitat, of its flow, of its living conditions, right? And we often can find in regulated rivers that there is some kind of bottleneck. For instance, in this tries to explain that there's maybe not enough habitat for the emergent fry. It's okay with the eggs and within the gravel, but when they come up off the gravel and should start to grow a little bit more, that might be a bottleneck because of constraints imposed by hydropower in our case then. So it makes a big difference if one of these fishes is being killed, because most of them are going to die anyway, to be rude. And if you take out one of these, which is those that have gone through the density-dependent mortality stage, right? So this is something we have to keep in mind when we are looking at mitigation measures. Finding that bottleneck is crucial to know, and that might be quite different from each fish population and each river, because they're impacted in a different way. In other places, it could be spawning grounds that is a problem, habitat for adults, or whatever, or survival of eggs due to circumstances that are there. So keep that in mind. When we talk about main mitigation measures, of course we can do something with flow, and we have divided it in kind of 4 categories in this Fit Hydro project. You could adjust the habitat. If you have taken away a lot of the water, you might want to do habitat adjustments. And you might also want to help fish migration, both upstream and downstream. And don't forget that flow and sediments are connected, so we have to do something with the sediment management. If you have a dam in your system, you are for sure impacting also the sediment transport. I'm not going to go through all of these in very detail, but I'm going to briefly go through it. What we are trying to do is actually categorize what's out there, what has been used, what are the experiences from all these kind of measures, and I'll show you a method we're going to work on to put them together. Habitat adjustments can be made for all kinds of life stages, for adult fish, for spawning habitat, riparian zone. Well, that's not for fish though, but they depend on it. And all this list of different things that are done to adjust the habitat in an impacted river. It could be restoring. I'm not saying always restoring back to natural, but restoring the functions of the river perhaps. And they can be done in an extensive way or just in spots or in hot spots, and this is what we're trying to collect information about. You're probably all familiar with fish migration, and as we also heard a little bit from the plenary yesterday about fish migration, we should perhaps focus even more on the downstream migration, because making fish come up the river is not that complicated. Of course, there are many challenges of doing that as well, but making them come down, and like in this picture, where there is a hydropower intake in a tunnel which draws 70 cumecs, and then there is 3 cumecs going there. Which route does a fish follow when they're going down? It's obvious that it's more natural for them to follow the big flow, which is not such a good idea, because then they will go into a turbine and a 50-meter head drop, and they will come out as mashed fish, which is not such a good idea. There are many ways of stopping fish from coming in there, but all of them might impact the hydropower production. If you put a screening in front with small spacing, you change the head, and you will also get clogged by debris and so on. So we are looking at ways in Fit Hydro to find ways of doing this in a smarter way to prevent having an impact on hydropower and still guide the fish through the right way. Of course, every hydropower plant is site-specific, and not everybody has a setup like there is a tunnel here and a river with minimum flow release down there. They are different, so we're trying to find general methods that have to be site-specifically applied. We're not forgetting how to make fish climb upstream either. And many places there are solutions for fish upstream migration that are not working very well. Why not? It could be that they don't find the fish way. It could be that we have applied, as we have done in Norway, a lot of salmon type fish ways for inland fish that cannot jump like the salmon. So we have to change them. And this is also true for many places in Europe, that we have applied a technology which is not really suitable for the target species we are targeting. And maybe they have also changed operation mode on the hydropower plant from when they were built, so we have to look at better ways of building either nature-like fish ways or traditional fish ladders, and how do we design the entrance, where do we put them, and so on. There's still a lot of work to do on that, and I believe there's also many sessions here at the Ecohydraulics and for looking at this. As I said, we should not forget that hydropower always needs a dam somewhere or a big or large, and that will impact the sediment transport, erosion, and sedimentation processes in the river. In addition, you also alter the hydrograph, which also has an impact on the sediment. And of course, a typical example is that you change the composition of the house where the fish is living, because they are mostly living somewhere down here. They go up and down in the water, and they use the sediments. So if that change, of course, it has an impact. So we have to take that into account as well. However, it's very seldom that only one of these kind of problems or bottlenecks occur in a river. There are several challenges, and there are several ways of solutions. So how do we choose? How do we combine the best set of mitigation measures? And that's where we are trying to bring into something new into this, because it's not necessarily new to do one single thing of these mitigation measures. And how can we choose the best? And then we also want to take into account the loss or gain of power production and the costs related to this. Because that's of course important. We are trying to find a cost-effective mitigation measure. And losing hydropower production might be also very costly. But maybe with today, the way of using hydropower will be quite different in the future. We need to integrate a lot of, that's worldwide, a lot of other renewables like wind and solar energy. And hydropower could be excellent if we can use the flexibility in hydropower to fill in when there's no wind and sun, and maybe stop the hydropower when there is a lot of wind and sun power on the system. But how does that impact? How can we adapt that as well to be to the benefit of the ecosystem? And that might work, but we need some tools to do that. We have collected already a lot of information, and we actually need more on different mitigation measures. How much does it cost? We have looked at, there are many reports out there, not so much in the scientific literature, but in the gray literature, reports and studies like some of even the hydropower companies like Harby in Austria has done a very good comprehensive study of the cost of different ways of upstream migration measures. We can get some numbers out of it, and we are still collecting that from other. This is just an example of what are the costs, what are the average costs, and what is the generation loss when you did this, and so on, because you have to release flow. Not going to go through in details on this, but just showing that we have, this is just to show you that we have done some work, collecting some costs on these different things. It's not an easy thing to do because, as I said, every hydropower project is site-specific. So, but we might want to hit the range of how much does it cost to release flow, how much does it cost to build effective upstream and downstream fish migration pathways. And the same for habitat measures. So, how do we combine this? Well, we were thinking about doing the ideas of using the methods of Bayesian Networks. It might be a very good idea because it's a way of integrating several measures and using information that for one hand could be very detailed and for other hand just expert opinion to combine it. We can use all kinds of input data for it, even expert opinions. Of course, we are, when possible, using model outputs and detailed information. And we can also handle the uncertainty, which might be very important. There are some limitations in Bayesian networks about the spatial resolution and the temporal dynamics of it, but I think we have to live with that if we're going to use this method. We're still going to use also the method that you will think before you go out and dig in the river, though, but this can help you think. And the way we can do is like you can set up schemes like this. I'm not going to go through this because I'm not an expert in using this, to be honest. But the principle is that if you have a set of measures listed here, it's the same list or part of the list I showed you earlier. They can impact, or doing them can help sediment management, it can help migration up and downstream, it could be flow release, it could be habitat improvements. And these bars is meant to show that from a state of zero, meaning that it's not successful at all, to a full mitigation of the migration possibilities on these graphs. And of course, there are some of these measures that you do that can impact more than one. It can, if you release water, I'm sure that it also can help you both with habitat, both with migration and so on. And this is our job now, is to find actually the relationship to this, to how much do you have to do on this to move the green bar up and down here. So that's something we can use the Bayesian networks to. And then again, to how to get it all together to the sustainable fish population level. We also have to see how to choose the best combination of measures on migration, flow, habitat, and sediments to achieve. It sounds a bit complicated, and I hope it is as well, because as Einstein said a long time ago, all the easy things we have already solved. It's just the complicated left. So that's up to us to find out, right? Just zooming in on one of them, that's where these relationships come in between those mitigation measures. How does that impact habitat? And it could be described as different functions, either very simple 1 to 0 function like this one, or more complicated one depending on what kind of input data knowledge you have. So that's one of the strengths of these Bayesian networks, that you can add very simple functions and more complex ones. Okay, I'm not sure if that's very clear, but it will be more clear for the next Ecohydraulics. I think we can present results of having applied this already. Hoping to do that. What is also in the basics of this is that when you have found out what kind of measures you should do, what kind of solutions, which methods do you use to create that, we provide also tools that you can use to plan, to implement, and to monitor afterwards. And we also in FitHydro develop some nice new devices. If you apply for a project for the European Union, you also have to show your innovation capability. So there are several nice devices. We're also this is a new instrument to measure. It looks like a fish, or it's intended to look like a fish. I think you will also hear about that in other sessions here at Ecohydraulics. So showing the way of how to use this. This is what we do in our work package in this project to put that together. Finally, what could be the benefit for you then, or for maybe not for only scientists, but also especially for management authorities and for hydropower companies, is that we put together all these, we call them SMTD, solutions, method, tools, and devices that we are developing and testing in FitHydro. We use them to show what to use for different mitigation measures, and there we combine it with the cost and the effectiveness of them, and the system of using the Bayesian networks to find the best solution. And we also plan to give this out free, of course, for the public in a wiki. So you can find, I'm not sure if some of you are familiar with the Reform project, an important European project that was recently accomplished, has also a wiki-like or a website where you can see different mitigation measures. So it will be something like that, put together also with looking into the costs. Of course, we will do reports and articles and so on. And included in this idea is also making a decision support system out of that, which can add on for managers to see better how to use all this kind of information. This wiki, which we are going to make at the end, will have a sort of setup like you look at the problem, you remember the bottleneck, what do you think is a problem in my river, and then look for the bottleneck. Okay, why is there no fish here, or why is there the fish never grow big enough, or whatever the problem is. You will find a bottleneck, and then you have a list of potential mitigation measures, and point 4 is how to combine them and find the right. And not to forget that we also have to give support into how to plan to implement it, and not to forget how to monitor and maintain such mitigation measures. This was a little summary of what we are working on now. So I cannot present what I think I wrote in the abstract, some applications of having done this. Of course, you are always very, very optimistic when you write the abstract of what you will obtain at this conference. That will come next time, but we're on the way. So I just want to remind you 2 things that I think Not forget, we get the rivers we deserve. It's up to you to help society move from this type of rivers to this type of river, right? So if they're still like that, it's maybe also because we didn't push strongly enough in research and get the results out to the managers. How should a river look like? Right? Sometimes it's not possible to change it, but sometimes it's actually the lack of knowledge and lack of methods that hinders. So we all have to help on that. And then another, it doesn't help if we have this perfect river like this. Just remember that fish dies only once. So if there's a week with no flow here or something happens, then it might be catastrophic for the environment living there. However, also remember that it has not for sure a population effect. If one fish dies, it can have a huge effect or a smaller effect, depending on where you are in the life cycle and so on. So think about that as well when you're doing things combining ecology and hydraulics into ecohydraulics. Thank you.